Okay, we're going to continue, people. I need to take from this slide, okay, one fact that on this edge, let me change to this. Okay, on this edge, people, right, we have mx equal to 0. But since w is immediately exactly equal to 0 along this edge, right, because it's a condition, this direction is y. So this is 0. So an equivalent condition for this is that the second derivative in x direction on this edge has to be 0. Similarly for this edge, okay? Since the edge cannot move, w is exactly 0 along the x direction. So the second derivative in the x direction has to be 0. So if we need this to be 0, then the second derivative in the y in this direction has to be 0. Okay, so in this case, we apply these details for this case. Okay, so instead of mx equal to 0, okay, that's on this and on that, we can say that that's the second derivative. Let me write okay, here, instead of this, we can say w xx is 0. And in this case, is w yy is equal to 0. Okay, and we see immediately that this function, okay, if you draw, for example, for m equal to 1 and n equal to 1, which is the simplest case, okay, the function will be something like this. So this is for m and n value 1. So you see that immediately we satisfy this boundary condition. Okay, now if we differentiate twice this expression, we're going to have minus wmn m pi over x, and then we get the same sine m pi x over a sin n pi y over b. So along this edge and along this edge, wxx is equal to 0. So that's satisfied. And if we we get the second derivative of w with respect to y and evaluate along this edge and along this other edge, again, we're going to see that this is also satisfied. Okay, so this function here satisfy all boundary conditions completely. Okay, and all what we need to do now is to satisfy the equilibrium inside the plate, inside the domain. So that's what we're left with. Okay, so we have the w is, we suspect that it is equal to that, and that function satisfied all the boundary conditions. So all what we need to do is to replace this w into this differential equation. Okay, now we remember that the nabla 4 is equal to this, right? So this here is equal to m pi over a to the 4, to the 4, and the same w. This one here is equal to n pi over b to the 4th and w. And this similarly for this one here. So after we replace, we can eliminate from both sides sine, and then we can get wmn. Okay, so we're going to have here d, okay, m pi over a to the 4th plus twice m pi over a squared n pi over b squared plus n pi over b to the 4th times sine, and on the right hand side we have pmn, sine and sine. So we cancel these two with these two, and and here I need a w. So I need to take all of this to the right-hand side, and this is the result. So this is an expression for W, the amplitude, in the case of a sinusoidal load. Okay, just to be certain that we are okay, PMM has units of force over length squared. D has units of force times length. And I have 1 over length squared into the square. So it's going to be length to the fourth up here. So we cancel force. We have 2 and 1, 3. So we have length as a measure of the deflection. Okay, people? You see that's why we take this as the base case. Okay, so first we discussed that this function Wmn sine and sine satisfy all boundary conditions. And then we replace into the differential equation, eliminate sine from both sides, and we get an expression for Wmn which satisfies the equilibrium. So Wmn sine npx sine npy over b, it's a complete and exact solution of this case, right? And all what we need to be is careful with this, the m and n, they have to be integers. That's all. After we calculate the deflection, we can go on and try to calculate the bending moment in order to have finally stresses, right? So this is an equivalent expression in which we replace the Wmn, all of this is Wmn, okay? And we can proceed to differentiate like this, for example, for mx. So we have the second derivative. We don't forget, please don't forget this nu. And here I took a pi squared, and we cancel 2 with this. That's why I have pi squared down here. So this is the final expression, okay? And we see that this is like the amplitude, okay, of the bending moment, in this case, in the x direction, and the distribution is sinusoidal, right? So the loading is sinusoidal, the deflection is sinusoidal, and the bending moment distributions are sinusoidal too, okay? And finally, with the bending moment, we can proceed and calculate the stress distribution, right? So we can replace this into here, and we can evaluate over the whole thickness, varying this value of z, we can evaluate the stress in the x direction, okay? Is there any questions about these, people? Any questions? Any questions so far? Any question? No. Okay. After this, here I have evaluated the stress at the largest or the farthest fibers. So the farthest fibers will be at plus or minus t/2, right? So that's the farthest. So you replace here t/2, and this is what you get, okay? So that's the largest normal stress in the thickness, in a certain point where we have this bending moment. Now, let's use this in order to solve more complex situations, okay? And this is the case. Let's suppose that we have a simply supported, again, rectangular plate again, but now, instead of a sinusoidal, we have arbitrary load. Okay, it may have any shape that you can think. Okay, so for example, let's suppose that I can draw here something like, I don't know, maybe That's my loading. This is the loading. Okay? But since this is a linear, let me write it here. Since this is a linear problem, we can use superposition. So what we do is this. We express this function, which is really terrible, right? In this way. And we know that the solution to each one of these terms is equal to this. So that's solved. Okay? So if we do this, transform P or express P in terms of this sinusoidal series, we can take each one of these terms and we can set the solution. W is equal to WMN sine and sine, and WMN is equal to PMN divided by pi over 4, D, and all of that. So we know the solution for each one of these terms. So the step that we have to take is to solve this expression. So instead of P of X, Y, we have to express as a function, as a series. And what we need to do now is to deduce an expression for, or to calculate the amplitude of each term. That's all what we are left with. Okay, so this process can be completed if we can obtain an expression for PMN. That's all. So what we can do is, this is something that you did in series. When we analyze series, you multiply both sides by this term. So you have this term here, and you have this term here, and integrate over the whole plate. Okay, if you do this, if M is different than P, okay, this is different than that, or this is different than that, than Q, the integration will give you 0. You try. The only case that you have a result different than 0 is when M is equal to P and N is equal to Q. All the other results will give you 0. Okay, so we can write it here. Only for P equal to M and Q equal to N, we get result different and this is the result. Okay, you integrate, let me put it here, you integrate sine squared m pi x over a dx, this from 0 to a, is this equal to a over 2. Okay, so on the right hand side, you're going to have, since you have sine squared in x, sine squared in y, you're going to have ab over 4. Okay, and if you put this on the right hand side, this is the result. Okay, so this is the expression that we were looking for. EMN could be calculated in this way. And once you have this, you put it into here. Okay, and the solution for this was already solved in the previous subchapter. Right? So that's all what we need. You can take any loading from any loading distribution. You express that as the sinusoidal series. Any. How you can apply this expression to integrate, and you obtain PMN, and then you can proceed. The question is here, how many terms do you need? Well, that's the problem. Okay, because we don't have the time to wait until infinity. But That's something that you need to practice, for example, in your homework, in your assignment. Okay, so let's see two cases, which are the classical cases. Okay, so let's take a uniformly distributed load. So in this case, P of X, Y is going to be constant. And let's see what we obtain. Okay, so in this case, we see that P of X, Y is just one number. Okay, we can proceed. We can apply this expression. We can replace here a constant. We can take that outside and we can integrate this. People, integration is something that you learn in math. You know how to integrate. Now let's apply it. Okay, so that's what we do. So this is expression that we had before. So we put this into here. Put this into here. And then we can take that outside because it's a constant. What's the integral of sine n pi x over a? Let's ask somebody. Mr. Hidrobo, what's the integral of sine n pi x over a? Mr. Hidrobo? Mr. Hidrobo, not here. Mr. Pesantes, are you here? The integral of the sine.
And the sine is minus cosine.
Of what?
MPX over A.
No, it's A over n pi.
Okay.
Sine n pi x over a, and from 0 to a. Yes. Okay. You can do it. You can evaluate and all of that. Now, let's suppose that m is even. For example, m is equal to 2. Okay. If m is equal to 2, okay, we will have the 2 pi x over a. We evaluate that at a, right? So if we put a here, that will give us cosine of 2 pi. How much is the cosine of 2 pi? Ms. Valdez, cosine of 2 pi. Cosine of 2 pi.
1.
Yes. Minus cosine at 0, Ms. Valdez. What is the cosine at 0? Valdez, cosine of 0?
1.
So we get 1 minus 1 that give you 0. So when m is even, this will give us 0. When m is equal to odd, this will give you 2. Okay, so all of this is summarized in here. Okay, we have 2a over mb, that's this integral. This is the integral of that. For a over b, we have this. Oh man, here I'm missing the p. Here we should have a p. And this is the final result. But as we said before, m and n has to be odd. They has to be odd. Okay? They have to be odd. Here I'm missing a p. Please correct. I don't know if this is wrong in your class notes. I'm missing a p. Okay? Now, this is something which we said before. Okay, let me go back. Here, I have a series, an infinite series. This is infinite. The problem is that we don't have the time to wait until infinity. But here, we see that PMN has these two subindices in the denominator. So immediately you see that as m and n increases, this here decreases. So for example, if you take this equal to 1 million, it's going to be very small, neglectably small, right? So in general, we cannot expect to have 20 terms for this expansion, right? Probably we need, I don't know, maybe 5 or 6 or something like that. in order to have these values here. If you go on, yes, but you can do it. But the problem is that the result, since you are dividing this by m and n, the result is going to be very small. In general, neglectable, right? So that's your answer. And please, m and n need to be 0. Okay. Now, as you see here, I have a larger graph. Okay. So let me draw just in the x direction, because otherwise I can get messy here. Okay, let me see. Okay, so let's analyze this only in the x direction. Okay, and you see that we have here, we have that m and n need to be odd. Okay, so the first one is m equal to 1. Okay, so if we take m equal to 1, so the variation in x is going to be sine of pi x over a. So we need to express, I'm going to put it in the upward because I don't want to get confused, okay? So please be patient with me. So we have something like this. There. So this is m is equal to 1. Okay? Now, the next term that we need to add is m equal to 3. Okay, so when m is equal to 3, this here will complete 3 half cycles between 0 and a. 3 half cycles. Let me change color. Okay, so let's use green. So we have more or less like this. So we have 1 half cycle, 2, and 3 half cycles. Like that. Okay, now let's suppose we add them up, and you see that this from here to here, this is negative. From here to here, this is positive. Similarly, in this case, so if we add, we're going to have. Let me change the color again. Is in this part we increase up to here. Is and like that. And you see immediately that I'm cutting from this part and I'm adding in these other parts. Okay. And in general, this is a uniformly distributed load. That means that at the end, the value that we need to obtain is like a constant. Okay. So this, I'm going to write it here. Okay. This is the value that we are trying, the distribution we're trying to obtain. And you see that in this area, we are a little bit below. Here we are below, and here we are above. Okay, so that means that if we include the m equal to 5, we're going to include a bit more here. This is going to decrease, this is going to increase, etc. So as we increase the number of odd terms, in this case, we're going to get closer to the uniformly distributed load. That's what we need. Okay. So you can do something similar in the y direction, and you will see that that's the type of behavior that you need to consider. Okay. So according to the shape of the distribution P of xy, you need to obtain values of PMN, right? For example, if you have a symmetric load, okay. For example, P of xy is symmetric. Okay, in that case, you need to represent that with a series. Okay, and of course, each one of the terms, the sinusoidal terms, need to be also symmetric. Okay, needs to be represented by sinusoidal okay. You see here that the blue and the green both are symmetric. Okay, so you see that on this side, you have the same as in this side. On this side, you have the same as in this side. Similarly, for m equal to 1, this is equal to that. So you see that this is a symmetric function. So in this side, you have the same as in this side. Okay, so people, be careful, okay? Because if you have symmetric load, the resulting terms, the sinusoidal terms, need to be also symmetric. Makes no sense, right? If you have a symmetric load, to try to represent it with asymmetric load, sinusoidal terms, okay? For example,
I have a question.
Yeah, go on.
When you refer about the symmetric load, you mean that is the similar from the direction of x and y, or just from the
both? Yeah, remember this is a 2D problem, so you have to worry about what happens in x and also what happens in y, definitely. In this case, I don't want to draw more because I have a already complex plot, but you can also draw analysis using this line. And you see that in this case, in the uniformly distributed load, what happens on this side is the same as what happens in this side. Okay, so that means that if you have this line, okay, that's why you need this term here to use only odd terms, because when you use odd terms, the sinusoidal terms are symmetric with respect to this line. Right, so if you say that P of xy is symmetric, that needs to be represented with symmetric terms. If it is asymmetric, then it needs to be represented by asymmetric terms. Makes sense. Okay, Ms. Santos?
Okay, and when we have the uniformly distributed load is for the number of the m and n are similar?
Basically, that depends on the ratio, A over B ratio, right? But I wouldn't say I prefer one or the other direction. I would use the same number of expansions in both directions. So M should be similar to N in general. If you have an extremely difference between A and B, in that case, yes, I would prefer to use more terms for M than for N, or vice versa. But in general, I would use mostly the same numbers. Santos?
Okay, doctor.
Okay. Here, after we have done this, we can replace, okay? So instead of EMN, we have replaced this for PFXY. So we can take each one of these, apply to the plate, calculate the response, and then what we can do is simply add. So to calculate the response, this is the amplitude of the deflection. And since PMN, we have a formulation for this. And this is what we obtain. Please be careful, because this is specifically for the uniformly distributed load. Okay, If you have a different loading, then you have to replace this by the correspondent function. Again, WMN is the amplitude, right? And you see that I have M and N in the denominator, and I have M and N to the 4th power in the denominator. So you see immediately that as you increase M and N in the denominator to the 5th power, this is going to decrease very rapidly. That means that for WMN, probably you will need maybe 1 or 2 terms, and that's all what you need. Because the M and N have a high exponent and are in the denominator. That's not always the case, right? But this is the case for the uniformly distributed load. So that's something which is very interesting or very useful, because you don't need to include 20 or 30 or 1,000 terms for the expansions. Okay, for example, in this case, this is something that you have in your class notes. I expanded PMN, and this is the result. So remember, both terms need to be odd integers. So we go, for example, up to 7. So I change M, I keep it with 1, and I change N. Then I change M to 3 and keep changing N, etc. For each one of them, I'm going to calculate in the PMN. And you see that this is 326 to the 4th power. And down here, this is about 50 times smaller than this one, more or less. So it's a big decrease, right? So yeah, we could use up to 9, but probably they're not going to increase much. And here, I have a figure with the combinations, right? The idea is that PMN would be completely uniform. Okay, so that means that this is what we try to obtain. Completely uniform loading on the plate. But you see that there are some maximum values, and also there are some troughs here. So this is larger than this is smaller than that. But in general, as we can expect, in general, WMN, okay, doesn't change that much. So we don't need that many terms for the deflection, okay? For the loading, yes, yeah, we need more terms, but not for the deflection. This graph, yeah, it tells you a lot, right? Because you can see that I have a Mach 1, 2, 3, 4 maxes. That's what we have here. We have 7 half cycles, right? So that's, we have 3.5 cycles. That's why we have 4 max in both X and Y, okay? So that's something that you need to do in your homework, okay? Again, after we have calculated PMN, okay, we have this. We can apply this formula for WMN, and this is what you have in your class notes again, okay? And you see that in the denominator, we have a larger power. That's why we see that this is 0.016, right? And this is basically nothing, right? So you see here, using one term, only one term, 0.017. And here you have 0.016 using all of these terms. So that means that this is a good approximation for this result. But please, this is only valid for uniformly distributed load, okay? Now, how many terms? That depends on the proportions of the plate and also, of course, the shape of the loading. So basically, what you have to do is you have to trial and error. That's all what we can do. After having WMN, okay, after having this, you can apply the expansions for both derivatives. This is what you have again. You see that using one term, okay, and in y direction, I got 1277, and using all of these terms, you have 1146. So I would say this is a nice approximation, right? Because the other terms, they contribute some, but then not that much. Okay, so if you have the time, yeah, you can do the expansion. Otherwise, you could use one single term to approximate it and use a safety factor, okay? But I have to insist, this depends on the shape of the distribution. So this is for uniformly distributed load, okay? The other loading that we usually have is concentrated force, okay? And in this case, the concentrated force, we have to apply a delta Dirac function, okay? So this is a delta Dirac, but in 2D. Okay, and we have units of 1/L squared. Okay, so if we multiply that by F, the result is going to be force per unit area as we were expecting. Okay, if we integrate that, okay, we replace this into here, replace this into here. You recall from your math course that that's something that we also did in the chapter 3. The result is going to be the evaluation of sine x and y in the position where you have this force applied. Okay, so this is the integral, and the result is this, right? So you have this is something that we explain in you have a function, and you have a delta Dirac here. Okay, the integral is equal to f at a. Here, but here the problem is that we have two dimensions. So xf, yf is the position where you have applied the force. Okay, be careful because this is positive, right? Because downward is positive direction. Any questions about these, people? No? One thing here is that this is my PMN for the concentrated force. And you see here that it doesn't decrease with M and N. That means that if you want to express this distribution using a sinusoidal series, then you have to use an infinite number of terms. And yeah, it makes sense because remember the delta function values infinite at the point of application, okay? But fortunately, remember that we need to estimate WMN, right? So even though PMN doesn't change, right? This here doesn't change, but we have M and N to the 4th power in the denominator. So even though this doesn't change, WMN, which is something that you need to calculate because that's the amplitude of the deflection, they do change, they do reduce. Okay, so they are decreasing as you go with M and N. Okay, so we have to be careful here because in general, PMN, they don't decrease with M and N. But after we apply this in the expression for WMN, the amplitude, they do decrease. So we don't need to increase, to include a zillion terms for W. Remember, W is what we need. We need to include a decent number, but not infinite, okay? Now, these expansions, okay, are very long if you do it by hand. That's why in the homework, you have to do it in a computer program, okay? So we have 7 minutes. I'm going to share the next assignment, if I can find it. It's being posted, so you have it already, so you can start. This part here, it has to be solved individually. Okay, so in the first problem, what I want from you is to review the deduction of this expression, of this equation, and then I want you to, what can I say, to do a summary of that, but try, instead of giving me a explanation and all of that, try to use graphics, right? Some of us are more graphical, right? So if you summarize this in a graphical way, you can see the relation and all of this. I think it's easier for you to keep this in your memory, okay? So it's a good point to recall the assumptions, the simplifications, okay, that we have to make in order to reduce the equation. Exercise 2 is just an application of Hooke's law, but I want you to keep in your memory that sigma is equal to E epsilon. Yeah, that's when we dealt with only one term of the stress tensor. But now we're working with 3 terms. Okay, so we have to keep track of sigma x and sigma y. Sigma x is different than sigma y, right? So we have to keep track of those 2 terms. And finally here, okay, let's suppose that we have a plate simply supported, and we have a load here with this value. The position of the application is here, and you have the 2 dimensions, okay? So I want you to do the expansion here of this function, and then I want you to select the thickness of this plate, right? So if you increase the thickness, of course, the stress will decrease. How much you need to include, how much thickness you need to include, I don't know. That's something that you need to tell me, okay? Can you see? Oh man, I don't know, what did I do? Okay, sorry. Okay, so not only that, okay, but let's suppose that there are 2 concepts here I wanted you to have in mind, is that, okay, you apply a force and you're going to have a maximum stress. And this maximum stress has to be below 70% of the elastic limit. So it's going to be less than 0.7 of sigma yielding. But also, you're going to have a deflection curve. So the maximum deflection, I don't know how, maybe it's possible that you have something like this, because you have here the application. So if you have the maximum, so W max has to be less than B over 20. So you have to select both the thickness in order to get the stress to be less than 0.7 of yield point. And also the deflection has to be smaller than B over 20. Okay, so when we design, what we do is we take what we call modes of failures. Okay, so there are several modes of failure. Okay, so even though you don't know this terminology, but what I want you to have in mind is that when you analyze and structure, at least you have to have in mind two things. Okay, the stresses are low enough and the deflection is low enough. There are other modes of failure that we can mention later on. For example, if you have something in compression, right, you have to be certain that the load, that the internal force doesn't get closer to the critical force. For example, in the case of the column, this is another mode of failure. In this case, we're going to consider two modes of failure. One is the strength. That means that the stress is less than a certain value. And the other is what's the name? That the deflection is below this limit. Okay? The first one is more common to consider, but the other we shouldn't forget. Okay? So the stiffness, I'm sorry, I forgot that word. So you have to consider the strength and the stiffness. So we don't want the stress to be close to the failure, but also we don't have the deflections to be too large, right? If you see something that it deflects a lot, even doesn't fail, but you see that it's a large deflection, and you feel like, oh man, that's a lot of deflection. Okay, so we have to consider both aspects. Okay, any questions about these people? For this, I need you to do programming because otherwise Excel is not enough. Okay, so you learn how to program a computer in a couple of years ago. So I want you to do it again. And in this case, since you learned Python, that's the language that you need to use. Okay. Mr. Paredes, do you remember how to program in Python? Paredes? Daniel Paredes, do you remember how to program in Python? No? Mr. Kimi, Elvis Kimi, do you remember how to program in Python?
So, Doctor.
Good. You need to start right away this weekend. Remember, you have your class notes from computer programming. That's a couple of years ago. Take the dust out of those class notes and
Doctor,
try to restart again. Mr. Llanos, you have a question?
Doctor, sí, I have a question. Can we use the MATLAB? Or... No. Only Python.
Only Python.
Okay.
You learn Python, we are going to use Python. That's all. Because otherwise, the assistants will have to review too many things. Please be careful. Since you have to do this, that means that I can ask you something about that in the evaluations. Okay? It's not that complicated. This is a simple thing to do. But I need you to start doing it. Okay? Okay, people, I have a council here right now at 9 a.m., so I need to go. If you have questions, send me an email. I'll try to help you out. Okay? Bye now.
Thank you.
Thanks, Doctor.
You're welcome.
Thank you, Doctor.